we can actually just, in our case, compute a expected efficiency and high-level estimates of the coincidence rate. Now, the way that we do this is just following this paper that we found online with Newman et al. And this is a paper from 2021 describing how to predict raw key rates, secret key rates, and QBERs for continuous wave pump UBM92 systems, which we are using. So what they do is they take all those physical parameters and they first compute the coincidence efficiency given these two parameters, the detection resolution time and the coincidence window. Now, the coincidence window is something that you, the user or designer of the system, gets to set. This is how broad of an interval you can permit for two coincident events. In general, you want this coincidence window to be larger than the detection resolution time, which is this uncertainty in the detected time or the time that the timestamp that's associated with a detection. So you want a coincidence window that's wider than your detection resolution time, but if you make your coincidence window too large, it'll then start having more accidental counts, which will cause problems. Now, once you have the coincidence efficiency and all of the efficiencies from the previous slide, including the brightness, you then can calculate the coincidence rate or the number of pairs that are coincident in the rate that they are being detected on the detectors. And this is just a product of all of these efficiencies in our system. So as we have a big product here, if these efficiencies start to deviate from one, we start to have considerable losses in our system. Now, the probability of accidental coincidences will start to capture the number of errors that we have or false positives in this system. So this can be estimated using this mathematical expression to the right, where this approximation actually will overestimate the probability when the photon loss is low. This will actually introduce errors in the theoretical model when the experiment starts to deviate from this high loss regime. So the next step is we can then calculate the rate of the accidental coincidences using this probability, and then calculate a rate of the total rate of coincidences, which is the rate of coincident pairs plus the rate of accidental coincidences. So we now have a rate at which we detect coincidences at our detectors between Alice and Bob. Some of those are attributed to bona fide entanglement witnessing events, and the others are attributed to accidents, which cause errors. So now we need to calculate the quantum bit error rate and the asymptotic secure key rate, which are the two main metrics of key distribution. So we use these rates that we just calculated on the previous slide to actually calculate these. So first, we note that we have this optical error rate. So if there's any probability of a bit flip in your system, then we will have a optical error rate associated with it. So as we introduce more optical errors, whether it's noise in your entanglement source or otherwise, we will have some contributions to this optical error rate. Then, as I was saying before, there's also these accidental counts, which also introduce errors. And finally, we have the raw key rate, where half of our coincidences are in the wrong basis and get thrown out, while the other half are in the correct bases between Alice and Bob and are kept. So that's why there's a factor of half scaling it back. So once you have all of these rates estimated, you can then estimate your quantum bit error rate, which tells you the quality of your quantum signal that you're using to distill a key from. Now, once you have the quantum bit error rate, you can then use the standard equation for the asymptotic secure key rate, which tells you how over a long time, if you're distributing lots and lots of keys to perform this process many, many times, how quickly can you, or what is your rate for this key establishment or secure key distribution? And this standard equation is shown here to the right. It depends on the binary entropy of the quantum bit error rate. So as there is more uncertainty in the quantum bit error rate, there's more errors. And what that means is that this binary entropy increases and the overall secure key rate decreases. Now, you might have heard that quantum key distribution is no longer secure if the quantum bit error rate goes above 11%. That is because the binary entropy becomes so large here that when it's subtracted off 1, the key rate is effectively 0. So if you have too many quantum bit errors, meaning you have more than 11% of your bits are errors, then you won't have any secure key rate to be established. And that is why we need to have a very high fidelity in our established in our entanglement and the quantum resources we use to establish secret keys.